The minimum number of stages, Nm, can be determined using the Fensky equation. The equation is given by Nm is equals to log times xld over xhd times xhw over xlw over log times kilk over kihk minus 1, where xld is a mole fraction of the light key in the distillate zero point 0.2. XHD is the mole fraction of the heavy key in the distillate zero point zero 0.01. XHW is the mole fraction of the heavy key in the bottom 0.25. XLW is a mole fraction of the light key in the bottom 0.002. KIL key is the distribution coefficient of the light key 1.5519000682, and KIH key is the distribution coefficient of the heavy key 0.8244154605, and this can be seen in the table 4. Using these values, the minimum number of stages calculated is approximately 11.36883833. Since the number of stages must be a whole number, it is rounded up to 12 stages.
The data presented in Table 5, detailing the minimum reflux ratio, can be determined using the Underwood equation. According to this equation, the minimum reflux ratio for component I can be calculated using the formula R min equals alpha I x sub d all over alpha I minus theta, where R min is the minimum reflux ratio for component I, alpha I is the relative volatility of component I, x sub d is the mole fraction of component I in the distillate, while theta is a parameter determined by the trial and error with a value of 1.4 in this case. To find the total minimum reflux ratio for the system containing components C2 to 7, the individual minimum reflux ratio are summed, and the final minimum reflux ratio is then obtained by subtracting 1 from this total. To calculate the actual reflux ratio, multiply the minimum reflux ratio by 1.5. This adjustment accounts for inefficiencies and provides a practical operating reflux ratio. The variable x is calculated using the formula x equals r minus r min all over r plus 1, where r actual is the actual reflux ratio and r min is the minimum reflux ratio. Next, y is determined as follows, which is y equals 1 minus x to the power of 0.33. And finally, the theoretical number of stages can be calculated using the equation n equals n sub m plus y all over 1 minus y, where n is the theoretical number of stages and n sub m is the minimum number of stages. This comprehensive calculation process is crucial for designing an efficient distillation column, ensuring the desired separation is achieved with a feasible number of stages and appropriate reflux ratio.
To calculate the liquid viscosity, we use the equation from Paris Chemical Engineer's Handbook 8th edition. Viscosity is equals to the exponent of C1 plus C2 over T plus C3 ln T plus C4 times T to the power of C5, where viscosity is in Pascal seconds. T is the absolute temperature in Kelvin. Given the temperature of 120 degrees Celsius, we convert it to Kelvin as 393.15 Kelvin. The values of C1 to C5 are constant provided in the handbook. As indicated in the table, we convert the viscosity from Pascal second to centipoise, using the conversion factor of 1 Pascal second is equals to 1000 centipoise. To calculate the average viscosity, we sum all the viscosities in centipoise and divide the total by the number of components. This calculation yields an average viscosity of 0.12118 centipoise. Another calculation shown in the table involves the finding the weighted average viscosity, which is the summation of the viscosity of each component mul- multiplied by its mole fraction in the feed. This calculation results in a value of 0.0185 centipoise. Next, we will be determining the column efficiency. The column is calculated by using the equation efficiency is equals to 51 minus 32.1 log times the relative volatility of light key, which is 1.88242546, times the average viscosity, which is 0.0185, and we will get now the column efficiency with a value of 97.8053%. For the calculation for the height of the column, we will use the equation height of the column is equals to NA minus 1 times C plus NA over 10 times C plus 0.1 times height of the column, where C is the assumed trace spacing, which is zero point 0.6, and NA is equals to number of actual stages over column efficiency over 100. So we will now calculate first NA, where NA is equals to 21 over 0.978, and we'll get the value of 22. And now, we'll now calculate the height of the column, where height of the column is equals to 22 minus 1 times zero point 0.6 plus 22 over 10 times zero point 0.6 plus zero point 0.1 times height of the column. We'll use shift solve in the calculator and we will get the height of the column is equals to 15.46 meters.
Moving forward to the second segment of the equations, the mechanical engineering calculations. So you might be wondering as to why mechanical engineering calculations are involved in creating a design for a MCD. Though we are chemical engineers, right? So we are thinking that it might not be covered with our scope or with our classes right now. So for the reason for that is that mechanical engineering calculations are crucial in designing multi-component distillations systems because they ensure the safe, reliable, and efficient operation of the distillation column and its associated equipment. So let's dive in first if we solve for the vapor mass flow rate. So here you can see that the vapor mass flow rate is represented by V and then is equals to the distillate flow rate multiplied by 1 plus constant 1.2838. So you can see here that our distillate flow rate is 44.7097 kilomole per hour, and then 1 plus the constant 1.2838. Then your vapor mass flow rate is 102.1080129 kilomole per hour. So after that, you can now solve for the liquid mass flow rate from the enriching section, which is LW top is equals to V minus D. So LW top is the liquid mass flow rate or enriching section. So it becomes so our enriching section is 57.39831.286 kilomole per hour. And then for the stripping section of the liquid mass flow rate is um, the bottom flow rate plus the vapor mass flow rate. So our bottom liquid mass flow rate is equals to 157.40 or yeah rather. So next is to solve for the factor flow for the top and bottom section. So solving for the flow factor of an MCD is fundamental to designing an efficient and effective distillation process. So it influences every aspect of the operation, from equipment sizing and energy consumption uh, to product quality and process control, thereby ensuring safe, reliable, and economically viable operation. So these flow rates at the top and bottom of the column are critical inputs for designing and sizing the distillation column and its internals. So to solve for the factor flow of the enriching section, so we have the FLV top or the factor flow of enriching section is equals to the liquid mass flow rate over the vapor mass flow rate multiplied by the density of vapor on the top over the density of liquid at the top as well. Then quantity of uh, exponent of zero point 0.5. And then we substitute all the numbers that we had. Then we are going to get the factor flow of the enriching section, which is 0.169 or 0.17. And then for the stripping section is the same, though the difference is that you only use the bottom datas. So for this one, we have the factor flow for the stripping section is equals to 0.53.